nanometer is extremely small. Second of these is that at the nanometer size scale, things can behave differently. Third, we can harness these new behaviors to make new technology. So the three things I want you to remember about nanotechnology are small, different, and new. The nanometer size scale is small. When things get small, they get different. We can use those different behaviors to make or improve technology that exists. Another way that we can talk about nanotechnology is that it's part of the metric system. Nano means a billion. A nanometer is something extremely important to nanotechnology. A billionth of a meter. 1 times 10 to the minus 10. But again, chances are that a 1 and a bunch of zeros or scientific notation isn't really helping you to comprehend how small the nanometer is. So we're going to do a couple other ways of thinking about it. One of these is by a colleague of mine who has a good sense of humor, Charlie Tan. So we're going to step down scales of thousands. We'll start out with Mini-Me from the Austin Powers movie. Mini-Me is about a meter tall, so 1 times 10 to the minus 0. We're going to look inside Mini-Me's eye at the things that let Mini-Me do the evil things he does. And we'll step down to the scale of 1,000, to the world of a millimeter, 1 times 10 to the minus 3. We're going to look inside that chip that's inside Mini-Me's eye that makes him evil, to the world of the micrometer, 1 times 10 to the minus 6. Sometimes it's also called the world of the micron. So micron, micrometer, they're the same thing. Now I think this is a particularly interesting world because it's the threshold between what we can see with our naked eye and what we can't see. So hair is in the world of the micrometer. Ranges from 40 to 80 microns, and we can all see hair. But other things in the micrometer world, like bacteria, we can't see with our naked eye. We need a microscope. So the micrometer world is very interesting because it's the border between what we can see and what we can't see. We'll step down one more scale of 1,000 from that to the world of the nanometer, 1 times 10 to the minus 9. Down here we're in the world of carbon nanotubes, buckyballs. We're also in the world of DNA, viruses, assuming we're all quite familiar with that. The nanometer world is also the world of atoms. If you were to line up 10 hydrogen atoms side by side, they would be 1 nanometer long. So the nanometer world is extremely small. And I'd like to emphasize that in order to get there from our everyday world, we had to step down 1, 2, 3 steps of 1,000. So it's extremely, extremely small. A couple other fun ways to think about nanotechnology. I'll give you a minute to read this. I can translate it. In the time it takes to read this sentence, your fingernails will have grown approximately 1 nanometer. So I want you all to look at your fingernails and then look away. Did you see anything? Can you imagine working with things that are so imperceptibly small? That's what scientists who work on a nanoscale do. They work with things that small, that tiny. And I'm also hoping that, because this one is a fairly easy one to remember, that in addition to small, different, new, you can remember this and share this with people afterwards when you leave the laboratory. Another, we do comparisons. So if you could take a gallon of paint and paint it 1 nanometer thick, how much area do you think it would cover? How much space? Think about how much paint it takes to paint, say, your living room or your kitchen or bedroom at home. Okay, do I have any guesses from the audience in this room about how much space they think it would cover or area? What was that one? Half a, okay. Any other ideas about how much area this should cover? Okay, well, it covers actually my entire university campus. And I know you don't know how big that is, but it's 3.8 square kilometers. So that's a pretty big area, 3.8 square kilometers. And if you think about that, do that? How would you take paint at 1 nanometer thing? How would you know if you did it? Would you be able to see it? And then another thing to think about is, there are lots of reasons why this wouldn't be possible. But one of the reasons is that molecules of paint are probably bigger than a nanometer. So you couldn't do it just because the molecules of paint are too big. So just to emphasize how extremely small this is. So nano is small. Why? Why do we do nano and why do we care about it? Well, I mentioned earlier that when things get small, things get different. Smallness can lead to new properties. And here I'd like to talk about a few of them. One of them is color. Color can change. An example of this is gold. So on the right we see gold, yellow, shiny, metallic. That's what we see in our jewelry and statues and things around us. However, if you get to the nanoscale with gold, that doesn't look yellow and shiny anymore. Lots of flash of nanoparticles of gold. So extremely small pieces of gold in a liquid. And it looks red. It looks like a juice. It can also be purple or blue. We'll talk more about that later. Melting point can also change. The melting point of gold dramatically changes when it approaches the nanoscale. So that's another feature that changes. Strength. Things can get stronger at the nanoscale. Conductivity. Things can become more conductive of electricity at the nanoscale. Lots of different properties. Reactivity. Things can become much more reactive at the nanoscale. An example of this is aluminum. So if you had a can of soda today at lunch, you probably felt fairly safe drinking your Coca-Cola or Coca-Cola Light, right? However, if it were nanoscale, aluminum can spontaneously combust. So dramatic difference. We don't have to worry about our pop cans or soda cans exploding in front of us. For the nanoscale, that might happen. So very, very different things, completely unexpected behaviors. So what do we do with these big behaviors? Well, scientists are thinking that there's lots of potential. And where there's lots of potential, there's lots of jobs and careers. A significant amount of money is being invested in nanotechnology research. To do research, you need people. So people to do the job, to lead the industries, and carry out the work. Some of the areas where we think there's dramatic potential is in medical applications, information technology, or IT, energy solutions, and water desalination, clean water. We'd argue that these are all very, very important problems and issues for the world today. And there's hope that nanotechnology can maybe help us address this. Not guaranteed, but there's hope. So how do researchers work at the nanoscale? If it's so small, how do they do it? I mean, we looked at our fingernails, and we couldn't even see anything. So how do researchers work at that extremely small scale? Well, they use something called a scanning probe microscope, or SPM. And things at the nanoscale are actually, I've talked about that they're too small to see, but they're also smaller than the wavelength of light. So you can't even use a regular microscope, or a regular optical microscope. You have to use something different. So you use a different sense. We talk about feeling a surface. You're not actually touching it with your fingers, but sort of feeling a surface. And a way to think of it, if you know what a record player is, for those of us my age and up, if you know what a record player is, it's like a record player, where you have an extremely fine tip running over a surface, moving up and down as it interacts with the surface, going over hills and valleys. If I had a row of you come and stand up here, and I didn't know who they were, and I closed my eyes, and I ran my hand over your head, I would be able to know who the tall people were and who the shorter people were, just by running my hand over. I can feel something. It's the same kind of thing. Researchers at the nanoscale use an extremely fine tip and run it over a surface. This is an image or a schematic of what a scanning probe or SPM looks like. And there are 4 main components that I want to talk, or 5 main components that I want to talk about with this. The first of these is the cantilever. You can think of it like a diving board. That it's the thing that connects the tip to the holder. It's very kind of springy, and it can move up and down, just like a diving board. The second part, that's connected to the tip. The tip has to be extremely fine and extremely sharp. It has to be as fine and as sharp and as small